explores the practice, right? So the idea is, if we can count the social distance, then we can further narrow down the scope. So as I said, we can try to look at how many interactions they have. So we can check like how frequently they tweet and mention or follow each other. But that kind of social networks is really sparse, right? So we can also model the implicit social correlation by doing topic modeling of their history data. If their history data, they often talk about similar topics and share similar opinions, then that means they are implicit friends. Okay, so we can do this by comparing the relation between the users from Chinese Twitter and English Twitter, and then we can narrow down the scope into only 1%, but we still keep all our targets in our scope. Okay, so that means we have some reasonable amount of data from the which is not under censorship. We can discover our targets. Okay. So now the problem is, okay, we have the targeted data, but where is our target? Okay. So our idea is we want to discover something we call as heterogeneous information networks from the data under censorship and not under censorship. So it's called heterogeneous because the node and the edge in this network, they both have multiple types. Okay. So for example, this is the moth and this is target. You can see it has a justice event with another entity, and it has a family relation with the symbol gua, and you can traverse through the network. Both can link to China. So so you may wonder, how can we discover this network automatically, right? We can apply all kinds of natural language processing techniques. We can do semantic relation injection so that you can get the family relation. You can do event injection so you know the top employee and the justice event. Also, we can do semantic role labeling so we know what kind of roles these different nodes played in different sentences. And if these results are too bad, then we can also rely on very coarse-grained co-occurrence to see how likely they appear in the same sentence. Okay, is this clear so far? So we can construct these networks automatically, use all kinds of text mining, natural language processing techniques. But you can see, you can imagine the network might be very noisy, right? Because all these steps are automatically done. So that means if we just count the number of edges or like number of neighbors, we might get very unreliable results. Okay. Of course, you can put all kinds of confidence value, the probability to each path. So now the key issue is how can we determine which node is our target? For example, when we have a network like this, we need to decide whether Earth common is our target, or CCP is our target, or Berkshire is our target. Okay. So this becomes the question: what is the shortest path we can walk from the moth to the target, right? Okay, so to compute the distance, we can count how many common neighbors they share. If they share more common neighbors, it's likely they are a pair. And we can also check how many paths we can walk from one moth to the target. If there are more paths we can go from moth to target, then they are likely to be the pair. Or we can pick up the traditional random walk techniques. We can check how the probability we can walk from one node to the other, right? And or pairwise random walk, we can check how likely they reach the same node. So if you look at these formulas or these different metrics, they all ignore one fact, which is how popular the moth and targets are, right? For example, if the moth East West King is here, and if I'm the target node, then it's very unlikely for him to refer to me. But it's not because it's the probability for walk from him to me is low. The reason is because I'm so unpopular in social media, but he's so popular in social media, right? But if you look at these formulas, they did not take that into account. Okay. So what we don't like to do is we want to not only look at this kind of relevant context, we also want to look at other irrelevant context, like everything go to T and everything go to morph. So the first metric we took is called KR distance. The basic idea is we also look at other contexts so that we can do some simple normalization by incorporating the different context, irrelevant context. And also we propose a new metric called path same. The idea is we checked how strong they are connected to each other by looking at the paths, between M and T. So this is similar to random walk. At the same time, we also check how popular each node is by checking how many other nodes can reach M and how many other nodes can reach T. Okay, so we can see from this formula, this part try to capture the connectivity, and these two parts try to check the popularity of the nodes. Okay, is that clear? Yeah, so by doing this, we can try to incorporate the popularity and also the contribution of everything inside the path. Okay, so we call this as a map path because you can reach from the morph to a target, goes through different paths, and they have different types of facts. Okay. So we evaluated the results based on 133 different queries from Chinese Twitter, and we used English Twitter and Chinese messages from English Twitter as our background data, which is not under censorship. And then we also look at the web documents that are embedded in the URLs of Chinese Twitter as our background data. So what we are interested to check is how likely we can pick up their target if we look at top 1 or top 5 or top 10, right? Okay, so here are the results. If we only check the surface feature, for example, edit distance, because some targets, they just slightly modify their morph name, like by changing 1 character, 2 characters. If we just do that, we can get some targets right. For example, here, top 1, we only got 25% accuracy. And then if we add semantics, if we add the semantic relations and events, we can get a little bit of improvement. And then if we do the temporal distribution and try to look at the social correlation, we can significantly improve the results. And then if we add the heterogeneous information network using the new metrics, the MetPath-based metrics, then we can get about 61% accuracy for top 1 and 76% for top 5. Okay, so we don't see any previous work who were trying to do this kind of task, so we don't know how good the results are. So that's why we went to ask human annotators. So we asked some Chinese PG students. I think they are very keen about political news. So they are basically reading the newspapers every day. So we asked them to manually resolve their morph. And surprisingly, they performed much worse than the system. They got only about 38, actually lower than 38% accuracy for top 1. So that means they.
So how do you compute accuracy? What's your labeled data? Do you have morph target pairs that are confirmed?
Yeah, so we verify them based on Wikipedia and based on external sources. So we are very sure they are right targets. Yeah, that's a good question. It was very hard for us to do the choose creation, and we tried a lot of crowdsourcing methods to create that. Yeah, for those 133, we are very sure they are correct. Okay. Yeah, so I think the results are promising, although they are not great yet. It's only 61 for top 1. I think if we sell this to Chinese government, they will give us millions of dollars. That's not our goal. Our goal is to understand how their internet language evolved over time. It's interesting, like a lot of morphs, they were derived from older morphs because these morphs will go to the blacklist of the government very quickly because they are doing the manual analysis of the information every day, right? So people have to be really, really creative. They have to keep changing these morphs. So you can see languages really evolve over time.
Is it a one-to-one mapping, or do you have actually a one-to-many?
Very good question. It's most cases multiple to one, right? Yeah. One-to-one case, we also saw some of them. For example, baby, right? The baby can refer to multiple partitions. I mean, sometimes one person become popular, the other become popular.
So they reuse the names.
They reuse names, but it's much less often than they change the names. They change the morphs. Yeah. And also, the challenging part is when the morph can also refer to the real entity. For example, the best actor. Maybe the message is really talking about the best actor who won the Oscar award or something. So we really need to look into the context to figure out it's really the morph or not a morph. That's the most difficult case. Yeah. If it's unique, it's actually trivial. Yeah. Okay. So, any more questions before I go to talk about other projects? Okay. So I would like to give an overview about other projects. So I was fortunate enough to be supported by a lot of government agencies, and but the coherent thing of my research is I try to discover more information, more accurate information from multiple sources. So I did this by putting all kinds of languages together and different genres and different data modalities. And my research has been regularly evaluated by some standard evaluation by the government, like NIST evaluations, and our systems consistently got top performance in the previous years. And also, I know many of you are interested in medical domain research. I did not do intensive research on that, but we have been collaborating with medical solutions, Siemens Medical Solutions. We developed a temporal event injection system for medical domain, and we got also top 3 performance in the I2B2 share task. Okay, so I would like to spend, I still have 5 more minutes maybe on other projects. Okay, so I said some information can come from multiple languages, right? So the idea is how can we extract information from foreign languages and translate them into English, for example. And we found that machine translation was really our bottleneck. Okay, so let me give one example here. The query is David Kelly, and we want to have an information generation system tells us where, which schools he was attending. And this is the machine translation output. Maybe I'll give you half a minute and you can try to guess the answer, and I will drink a little water first. You can just read this paragraph. Any clues? No? Maybe you can tell me, you can guess which sentence the answer might be located or something like that. Anyone has any possible answers? I cannot tell which.
Is that Google Translation?
No, I cannot tell you which system is from, but Mona knows which system this comes from. So this is one of the state-of-the-art MT systems. Anyway, so the correct answer actually comes from here, the free basket for trapping fish. Okay, and it actually talking about Oxford University. So I sat down the whole afternoon with the MT developer trying to figure out what happened here. And the only clue we got by checking each step of the complicated pipeline is that maybe the first character of okay, so by the way, this is from Chinese to English translation. So the first character of Oxford maybe have something related to the flea, because they co-occur in a lot of MT training data, and so they mistakenly translate the university name into this phrase. Okay, so we can see the challenge is if we want to find the information from MT output, they already missed a lot of information. We have no way to recover them, right? So what we would like to do is we want to have an MT system that really tightly integrate our information ingestion techniques so that they can give us accurate information translation. Maybe they can sacrifice something on the fluency and other not so important context, right? So what we did is that we want to retrain the MT by taking into account all the information. So what we did is we developed a bilingual name tagger so that we can, tag their source language and English side from their training data. So the training data is parallel coupled. Each pair is a Chinese sentence and English sentence. And what we can do here is we can take into account the features from the Chinese side and English side, and then we can also look at the bilingual factors are that aligned the two languages.